Can we coax bacteria to solve mazes and mathematics problems? Is it possible to engineer bacteria to add, subtract, and even identify prime numbers between 0 and 9? Our speaker today and his research team have this major and somewhat unusual goal to build intelligent bacteria. BITM, along with the Royal Society of Chemistry, Eastern India section, warmly welcomes you to the 25th Niroprova Memorial Lecture, Biocomputer and AI, the dawn of tomorrow's machines. Yes, a big round of applause, please. To share how clusters of bacterial cells in glass flasks can be harnessed to perform complex and abstract computational tasks, we have with us our distinguished speaker. I would request Director BITM, Shri Shubhabrata Chaudhuri, to please welcome him with a small felicitation. Let's have a big round of applause and join us in welcoming Professor Sangram Bagh, Biophysics and Structural Genomics Division, Saha Institute of Nuclear Physics, Kolkata. We look forward to learning from you, sir. Before we engage in this session, I welcome to the podium Director BITM, Shri Shubhabrata Chaudhuri, to deliver his welcome address. Over to you, sir.
Very good morning. The dignitaries on dais, especially Professor Sangram Bagh, those who are in the audience, the teachers, the students, and those who have joined online, ladies and gentlemen. On behalf of BITM, Birla Industrial and Technological Museum, I welcome you all in association with the Royal Society of Chemistry to the 25th version of Niroprova Memorial Lecture, and that is on a very interesting and contemporary topic that will get unfolded as we proceed with the program. You know that since 1959, this museum, which is housed in a Grade 1 heritage building, is a very, welcoming destination for visitors of all ages, especially for the students. And its activities are not only confined within the four walls. Even we reach out to the people in the far-flung areas in the eastern part. So we have a rich legacy. You go anywhere in the world, if you come across with the people, whether he or she is a scientist, technologist, or any other profession, you'll find that they always get connected in some way or the other during their student days with BITM. So BITM plays a big role in the formative years of so many people. And surely Professor Bagh also will share his very, fond memories of his association with BITM when he will be delivering his address. So you can think that coming here will definitely be one of the stepping stones of your career. With that, I would like to tell that, in fact, we live in an age when science fiction ideas move very, very close to reality. I repeat, I'm sure most of you, because whatever I will be addressing mostly to the students, because they are the major takers today. I am sure that all of you read science fictions. So whatever are written there, these are coming very close day by day to the reality nowadays. Let me inform you, just last Monday, the giant Google, the giant tech Google has launched one chip called Willow, WILLOW. Now the question is, what is this? What is new in it? You won't believe that any computational work, we do a lot of computational work in our computer. And we know that we are making supercomputers and they are doing great works. So, any computational work that even the supercomputer will take at least 10 septillion years. 1 septillion years means 1 followed by 24 0. So 10 septillion year means 1 followed by 25 zeros. Any computational work that any very updated supercomputer will take that much of time. This chip can do with Elan just in 5 minutes. So, are you feeling very breathless? These are the changes coming very fast. In fact, computing, that was a really buzzword now, but the scientists started working very seriously from the early parts of 80s. Lot of issues are still there. Major issues are there, they have got certain errors in their calculation. But still, with this chip, Google is claiming that error, that error is also within the limit of the threshold set. So in the coming years, lot of changes will come, and presuming that this is a big change because AI is all pervading. We know there was a time, even during our student days, we were not so much accustomed to the computers that way. So that time computer was the buzzword. Now AI is the buzzword. Lot of changes are coming. Even there is an area, that AI of AI. AI has already started working, but AI of AI is another area which scientists and technologists are working upon. Anyway, so presuming that such a big opportunity we have for the young students in the coming days, the United Nations declared 2025 as the International Year of Quantum Science and Technology. So, its aim is to celebrate the contributions of quantum science to technological progress. In fact, the topics today will cover a lot about it, because once quantum computing is introduced, lot of changes, lot of newer drives will be coming in drug delivery, in AI, and all the things. Anyway, let us come back to today's memorial lecture. Once again, I profess to thank you for joining us for what promises to be a fascinating exploration of an emerging frontiers of science, bacterial biocomputing. Just imagine that programming living cells to perform calculations and solve problems. These are the general tasks generally we or typically associate with computers. This exciting research takes us beyond the binary world of traditional computing into the realm of biology, where cells, like tiny organic machines, process the information in entirely novel ways. We are indeed thrilled to welcome Dr. Sangram Bagh, a scientist a very renowned scientist from Saha Institute of Nuclear Physics, and in its Biophysics and Structural Genomics division, who is leading this groundbreaking work. Dr. Bagh and his team has figured out how to program bacteria to work together, just like Lego blocks, to perform complex tasks. Dr. Bagh and his team have transformed ordinary bacteria into living artificial neural networks capable of identifying prime numbers, decoding complex patterns, and envisioning future applications like autonomous decision making in healthcare and climate change mitigation. Dr. Bagh will tell us how this works, why it matters, and how these tiny living computers might transform our world, especially your world and the future. So, my dear students, ladies and gentlemen, please give once again a big round of applause to Dr. Bagh for giving us the opportunity to listen to his very invigorating, work. Thank you. Thank you all. Now it is over to Dr. Bagh. Oh, over to Madam. Thank you.
Thank you, sir. Today's session will not have been possible without the initiative and generous support of the Royal Society of Chemistry, Eastern India Section. Please join me in welcoming Professor Sriparna Dotto, former Head of Department of Chemical Technology, University of Calcutta, and Vice President, Royal Society of Chemistry, Eastern India Section, to introduce us to the missions and objectives of the Society. Over to you, Madam.
A very good morning to all of you. Like previous years, the Eastern India section of the Royal Society of Chemistry, in collaboration with Birla Industrial and Technological Museum, has organized the 25th Niroprova Memorial Lecture today. Niroprova Memorial Lecture is arranged by Royal Society of Chemistry since 27 years in the name of Srimati Niroprova Banerjee, who is the beloved wife of the father figure of rubber technology, Dr. Dashurothi Banerjee. Niroprova was born in Midnapur in 1920. She lost her father at the age of 9 and came to stay at the house of her maternal uncle, Professor J.L. Banerjee at Kolkata. Later on, she was married to Dr. Dashurothi Banerjee. She was a benevolent lady who spontaneously helped needy children and students to pursue their studies and get established in life. Now, coming to Royal Society of Chemistry, it is a learned body, the oldest learned body, with more than 175 years of history and more than 54,000 members globally. Our mission is to advance excellence in chemical sciences on a global scale. We believe in the philosophy of catch them young, and we invest in inspiring the young minds to create interest in chemistry, to shape a diverse and skilled workforce for our future. Royal Society of Chemistry has 5 overseas sections in India. We, the Eastern India section, work with the students, scholars, and faculties of college, universities, schools, as well as the scientists and chemists of industries for the advancement of chemical sciences. Today's seminar on biocomputer and AI, the dawn of tomorrow's machines, seamlessly aligns with our goal. I extend my best wishes to the speaker, who I believe can really enchant you with his wonderful deliberation, and also hope that the students will not only be enriched, but they will also enjoy the lecture. Thank you very much.
Thank you, Madam. To delve into the nuances of biocomputing, we have with us a stalwart of synthetic biology. May I request Professor Shumon Mojumdar, Director R&D, Actelis, and Honorary Treasurer, Royal Society of Chemistry, Eastern India Section, to introduce today's speaker to our audience. Over to you, sir.
Welcome you all to this memorial lecture. It's my pleasure to introduce today's esteemed speaker. He is a distinguished scientist and he is working in the emerging field of synthetic biology in Saha Institute of Nuclear Physics. He has finished his BSc in Calcutta University, but post that he has finished his PhD in the University of Toronto, and followed by a postdoctoral research at MIT in this particular field of synthetic biology. And he has been conferred several fellowships. He is the fellow of Royal Society of Chemistry since 2022. In 2021, he has been elected as editorial advisory board member for ACS Synthetic Biology. And he has been also invited in several important invited talks across the globe. So with that, I invite Sangram to deliver his lecture. I think it will be very insightful. I don't know how many of you know that we have trillions of these bugs. We call it bugs, but they are actually beneficial bacteria in your gut and on your skin, which are living and which are there as we speak, doing very complex activities and making you walk and talk and think. And Sangram's team has actually will give you the magnification of that today. And hope you will enjoy the talk. Thank you.
Thank you, sir. We'll take just little time to clear the settings. Maybe request our delegates on stage to please take their seats in the audience while we set up the stage for the speaker. He'll be speaking on biocomputer and AI, the dawn of tomorrow's machines. Over to you, sir.
Thank you very much. First to the BITM, our director, sir, and Aditi ma'am for inviting me here and giving this opportunity to speak with you. Definitely Royal Society of Chemistry, who is in collaboration with whom these things are happening. So I'm really honored to be here. But this is not the first time I'm here. When I was at your age, when I was in the class 8 or 9, I couldn't remember. I'm too old now. So, and that time I came to give there's a science seminar competition. It happens throughout the West Bengal and nationally. So I represent my district, Birbhum. So, and that I talked very well, but the judges were not good, so I didn't get any prize. So, but anyway, so So yeah, so it happens to you also. I understand, but that happens in life. That's fine. So, when I'm going to talk about what we do, or biocomputer and something, you got a good introduction from our director sir as well as Shumon. The field, it is a part of a field, and this field is an emerging field. It's called the synthetic biology. So synthetic biology, if you actually go to the Google and just search for the synthetic biology, you probably find hundreds different kinds of definition. But what is the best definition I found from a student? And her name is Shreya. Shreya is an undergraduate biotechnology student from IIT Madras. And as so when you start your lab, you always get a lot of different emails from the students because they want to do some 2 months of research internship. You'll also probably do when you were in the college and universities, and they want to do. So you get hundreds of the mails almost every day. Kind of, they want to do that, and the whole thing. But you can take only 1 or 2. So you said no. So the same thing I did to Shreya. I said no. But then, after a week, I got a call from her HOD suggesting, no, Sangram, you have to take Shreya. She's a very good student. She's very interested in our work, and so on, so on. Still, I was so reluctant. I said, Shreya, this is a graduate institute. I don't have a hostel for the undergraduate students, so I don't know how to do that. So she said, no problem, sir, I'll manage my own. And she has nothing to do with the Kolkata, and she's from Chhattisgarh. So when she said that I'll make my own arrangements, and she's taking so much pain to just come to the SINP, so I had to say yes. So she came. And I asked Shreya, that why did you take so much pain to just to be 2 months in my lab? And then she told me a very interesting story. When she was a child, her mother gave her a few books as a gift, and one of the books is a Frankenstein, and it was amazed her. And from that time, she started thinking that if one day she could actually make a monster like that, and that would be great. That is very cool. And now she started thinking that if she comes to my lab, she will learn how to make a monster. Okay? So the synthetic biology, the best way to define the synthetic biology is a part of the science and the technology through which you can design and build a monster. Okay, and so when it calls the monster, I mean, if you can make a monster, you can make a god too, right? So if you can make a Thanos, you can make Thor too, right? So exactly. So we are exactly. So but start thinking about what our director sir was telling, that we are in a position where we start thinking that our science fiction is getting into the reality. And I will also try to show you that what science fiction did not think about, science can goes there too. Okay. So now this is so we are in the technological era, and we like to look at our future, or the future of machines, that how the future machines would look like. So here is the Bicentennial Man. This is a very famous novel, a story from Isaac Asimov, and it is a movie in 1999, I believe. And the whole idea of this movie, this is a robot, and this robot actually evolved by scientists. There's a robot, he started the robot and then start actually building on it and something new. At the end, after 200 years, it looks like a human. So what it looks like as a robot, this is again a robot, but it has all the human feelings and so on. So how we want to look like our machines, this is one of the characteristics that probably we want to have our machines like that. So that is on that level. Then I can take from this Asimov's case, there's another very interesting story, and that's called The Fantastic Voyage. That also, this movie is, I think, 1968 or 72 or something like that. In this case, the story is telling that there is a patient, and in this patient's body there is a wound where the surgeon's scissor cannot go. So, but that time there is a technology, this is science fiction, there is a fictional technology through which you can miniaturize everything in a very small thing. So that's why they miniaturize a set of doctors and nurses, okay, and put in a submarine. That submarine they also miniaturize, and here this submarine is then inject that submarine into a human body. And this is, you can see, this is the red blood cell, okay, and this is the submarine. And then these doctors and nurses came out, do their operations in that exact wound, and then the whole story is how it is coming out from the body because they've lost the root and so on. But what is important, we don't know that we have that technology we'll have ever, that we can miniaturize everything in that. But what we need, this story is suggesting that there is a need to some intelligent thing to be here, a small thing which can actually go and take a decision like a human, right? It could be human or it could be something. So we'll just try to understand that how those kind of the technology is possible probably within next several years or so. So let's start from a little history. Though it is a history and it is 1997, right? In this 1997, there is a match was going between a computer, it's named Deep Blue, made by IBM, and it's the Garry Kasparov. Garry Kasparov is one of the legendary chess players. Yeah, so now it's Gukes, right? Okay. So now this Garry Kasparov, but you can see what is happening here, right? Just from this picture, you can see what happened. This Deep Blue won the match, right? And this is a huge bang on the science, technology, the way we think, economics, and everything, the way our philosophy works. Because when we talk about a chess playing, in our human culture, chess playing is always connected to as a mind game, right? So that if you study Sherlock Holmes used to play chess. If you study Feluda or Bomkes, they used to play chess. So the whole idea that because this is the Mogojastro, because this is the signature of an intelligent people and the mind thing. However, when this happened, this suggesting that a computer now can think like a human. Okay, that's a different question. But what you used to thought, the human used to thought is the mind game. A computer is defeating a human, right? So there is a lot of. So this is the juncture where the two things are happening. The computer scientists started really thinking that it may possible that one day we'll make a computer which can actually think like a human. That is the Alan Turing once actually thought about that. The one day we can make actually a machine which can think, and this is probably a starting point. So therefore, you see the lot of computer scientists and lot of other scientists, other engineers, and different companies, different universities are coming together to start making the AI. Just a one point of caution: this computer is not AI. AI is little different than what this computers does. So if I get a time, we can discuss that. But this is not AI. But the idea of that we can think about more on making a thinking machine starts here. A second point is coming from the biologist. So biologist said this is a human brain, okay, and they're playing with a computer. That basically means the biologists started thinking, especially the neuroscientists, what if we start understanding our brain from a computer science point of view, a computer engineering point of view. So you'll see there is a lot of resources, a lot of scientists, and a lot of neuroscientists are changing towards the computer science. So today, if you study neuroscience, you will see it's not a biology, but it's just an engineering subject. Okay, so that is the change. It really happens. So what this basically tells, at this moment, we do not know a lot of things about the brain. We don't know how we imagine, how we think, and so on. But what we do know at this moment, that this brain has billions of the neurons, and they have trillions of the connections, and those connections are doing some computation to whatever we are actually doing at this moment. So there is another project, which name is the Blue Brain Project, and this is the IBM and Swiss Federal Institute of Technology. They're collaborating in this. And the idea is, so if we can simulate all these trillions connection in the computer, probably we'll know some more about our brain. So the results, it is not published yet. It will take some couple of years to get that. So we don't know how it will look like that time. But what we do know, that if you want to simulate a single human brain in the computer, the amount of energy it requires, and that is 10 to the power 6 watt. And this is the amount of the energy you can get from a mini hydropower. Okay, so which basically means this is a limitation in one sense, because have you seen this movie, Terminator? In this Terminator, this is a machine, right? But we cannot make that kind of a stand-alone machine, a robot, which have even like a human-like intelligence at this moment, because the amount of the energy it will take 10 to the power 6 watt. That means if you want to have a robot here, you must have a hydropower on his head, right? At this moment, we actually cannot do that. So that is. But how much energy our human brain takes? 20 watt. So which basically thinks, what basically tells that our brain, which is nothing but a biology, nothing but living cells, it will not only compute, but it also computes at the very high energy efficiency level, right? No machines can actually go down in that level. So that's actually tells us. So the whole thing is clear. One message I tried to say, that our brain computes. So a cell computes, right? So that is why it is a common knowledge. If someone actually do very good math, and at the same time we say, oh, he has or she has a brain like a computer, okay? So if he doesn't like, if that person is like me, he has a brain like a donkey, right? So the computer and donkey, so that's the way we actually look at it. Now question is but what happens if we go to the primitive cell? And that's the bacteria. Can they compute? Okay, to answer that question, we have to watch a movie, and that's the Gajini. Okay, have you watched? Okay, if you haven't, it's fine. I'm not recommending it. Okay, in this movie, the story is the Amir Khan played a role, and Amir Khan he had just some transient memory. Sometimes comes and then actually forgot everything, right? And at one scene, there is one scene was there. There's a truck. Okay, so if I remember, okay, so Amir Khan was chasing a person. Okay, a bad guy. He was chasing, and then a truck was coming from the other side, and that truck hits that bad guy. And exactly at that moment, the Amir Khan forgot everything, and he looked completely perplexed, right? So what this movie scene is going to tell us about the memory? This is telling that if you want to do an action, you want to take an action on the next step, you must have the memory for the previous step, previous time point. How? Because when Amir Khan was chasing that guy, he knows, oh, chasing. He remembers, I'm chasing, that is why I'm taking my next step. But exactly at that moment, he forgets everything. He don't know what to do. Should I take a step, or what are you doing? So that means that you have to remember your previous step in order to take the next step. That is this scene is actually talking about that memory. Now, what have we learned from this movie? Now we try to apply here in the bacteria. So here we cannot actually do that experiment, but we can do a thought experiment. What thought experiment? We all, at least you know something called chemotaxis, right? So the bacteria actually swim towards the chemical attractants. So let's do a thought experiment. Let's take a big beaker, that beaker, okay? And it's full of water. And in this full of the water, at the one side, you give a chemoattractant. Let's say it is a crystal of the sugar. So if it is a crystal of the sugar, what the crystal will do? Crystal will start dissolve, and then it will start diffuse, right? From this percent, it is coming there. That means the concentration of the sugar is high here, and it is lower in this side. And this side, you just put a bacteria, a single bacterium, okay? Now what will do? Bacteria will sense that sugar, and that it actually start swimming towards that sugar concentration, or the higher sugar concentration is there. Now what will happen? Because bacteria is a very tiny organism. It is a 2 to 5 micron. So that means whenever there is some little turbulence in the water, then this bacteria actually hits by the water molecules and actually goes in this direction. So if it goes this direction and still swims, then what will happen? Then it is going away from the food, right? So what it does, it stops there, okay, and then starts spinning, and then some water molecule hits here, that actually goes in this direction, and again it starts swimming. So if bacteria has to take the decision to swim or to not to swim, then it has to remember the concentration at the previous time point, right? So then it can decide if the concentration is higher than the previous time point, then it will swim. Okay, if it is completely other way around, if it is less, then it stops and starts doing that, right? Now, that means the bacteria has a memory. But interestingly, bacteria doesn't have a brain, and bacteria doesn't have a neuron, right? So how bacteria is getting this memory? This memory bacteria is getting through the molecular interaction. There's a lot of protein, genes, and things, and they interact in this. There is a molecular network, and that molecular network actually gives the memory. So there is in engineering, there is something called a control theory. Through the control theory, this can be explained. So I'm not going to that explain. The only point I'm trying to say that now you can think a bacterial memory in terms of the engineering terms, like in terms of the computation, in the memory, decision making, control theory, so on. So if that is possible, then this is also possible. You intervene as an engineer inside the biology. Okay, look at that as like a machine. That doesn't mean that biology is a same machine, what machines we are using, but at least we get some point to actually start engineering that. So if we start engineering that, we can do some marvelous thing which cannot be done in the conventional genetic or genetic engineering or the biotechnology. So what is silic? So for example, if you think about a computer, it starts with some physical layer, right? Means transistors and so on. Then you make some logic gates out of it, and those logic gates are connected to the modules, then computer, then network. If you try to look at the similar hierarchy in the biology, it starts with the protein and genes, then it makes some biochemical reactions. Biochemical reactions together make some pathways, it makes cells, tissues, and so on, so on. However, we do not know how these are connected. We don't understand, because this is the evolution tuned for the 4 billion years, but you know every rule here. So that's why if you take a whole genome sequencing of all of us, from just looking at this whole genome sequence, we cannot tell why C likes Shahrukh Khan and why I hate Shahrukh Khan. Right? So you cannot tell that. This is an exaggeration, but you cannot talk about just looking at this static information, that what kind of the disease is going to get, what kind of how a drug will affect on the body. We cannot actually tell all those things, right? So, but what if we take this protein and genes and make some biochemical reactions which will work as a logic gate? What does that mean? In electronics, let's say an AND gate. So A and B are present, and then then only if the C produce, then it will be called as an AND gate. But this A and B in the electronics, it is nothing but an electric current, or in terms of the voltage, whatever you say. Here in biology, we can think about this in terms of the biomolecules. If the biomolecules A and B are present, then it will produce a protein called C. Then we can think about the AND gate. So in this way, you can develop some of the biological logic gates, and when you actually connect them, you can develop a lot of different functions because you already know the rules here. So here, for example, when people started thinking about if we can actually develop some of the logic devices in the biological cells, people tried to develop, excuse me, half adder and so on. I'm not going to the details, but what I can to say, this is a electronic, or this is a logic gate circuit diagram, and this is the genes and proteins, the molecular genes and genetic network, through which you can actually get this kind of the function. So that is the whole point. So if we can do that, what will happen? Many things could happen, and some of them looks like a science fiction. So this is a movie called Oblivion. I don't know if you have seen that, but in this movie, this is an alien civilization. It is almost a machine attacked Earth, destroyed almost the Earth, and still not all the people. There are some people who are called rebels. They are actually trying to destroy the alien civilization. Now, this alien civilization made some of the drones. These drones will come to the Earth, and then they're looking for those rebels. So if they find there's a human, okay, and if that's it just scan the human and they find if it's the rebels, then it will kill that person. So that is why it is a sense and destroy drone in these things. So using the similar principle, what scientist has developed, the same sense and destroy drone, but not for the human, but for the pathogen. So here, what people develop, so we have the gut bacteria, as Sumon told, that we have the trillions of the bacteria in our gut. So if you engineer a gut bacteria in such a way that when a pathogen is attacking the human body, and then when the pathogen attacks the human body, it actually secretes some chemicals. So this gut bacteria engineered gut bacteria can sense that chemical, and then only it turned on to produce a peptide which is going to kill only that particular pathogen, not touching other bacteria like antibiotics. Okay, so this is an autonomous kind of a sense and destroy kind of treatment you can develop through that. People also try to develop some autonomous uric acid maintenance system. So there is a change in the uric acid in our body, and we go to the doctor gives some test and then gives some medicines. But here what you can actually do, here you engineer the cells. These engineered cells you inject in an animal, and when there is a change in the uric acid concentration, rather than the set point, then it will either reduce that uric acid concentration or it will actually increase the uric acid concentration to come to the set point. So those are the things you could actually do. So I'll just give other examples where synthetic biology can work. And you can see this is the potential of the synthetic biology in space, and this is not my poster, it is made by the NASA. So the whole idea, if you at this moment, when you go for the space travel, but for example in the Mars, the whole idea is that you are sending some human, it is not to just go there and come back. You want to make a research base there, so that again some astronauts can go, again scientists can go and actually do that. Because it will take a huge amount of time. It will go probably a year, or at least 6 months, and coming back another 6 months, and probably you stay there for 3-4 months. So that's a huge amount of time. And in this huge amount of time, you cannot take all the resources from the Earth. So imagine you want to have some, you went to Mars and you want to have some biryani. Okay? You cannot say your mom, just please send some from the Siraj in this Bagh circus. No, we cannot do that. Right? You have to cook that biryani, not that cook the biryani, but you have to get all the resources. You cannot take the rice from here, okay? You cannot take your mutton, chicken, or whatever. There's no veg biryani exist in the world, okay? But at the same time, if you want a Bengali biryani, you need some potato, some aloo, right? So that you cannot take it from here. You have to build everything on the Mars. And the idea is called in situ resource utilization. So whatever the Mars has, some of the carbon dioxide, some of the probably some water, some whatever the Mars crust was there, you have to use those and make your everything, starting from your mutton to your rice. And for that, people think about, we cannot take the resources, so what we can do, by synthetically we can engineer some of the organisms and in a vials, and then you can go, because they are replicative, any organism is replicative. So when there's replicative, and they will do everything for you, for making this road, the making some radiation resistant habitat, your food, your chemicals. So that is the probably the solution. So I'll give you just example. Nobody actually done that, but I'm just giving you the example what NASA Ames Center is working on. So they are developing, try to a self-healing building. Okay, so what does that mean? And self-replicating and self-healing building, they're trying to building from the fungus. So they program the fungus in such a way that will make a building, and based on the dynamic environment, how much ionization radiation is coming there on based on the, they will identify themselves and actually increase the wall thickness and so on. So it is a completely healing and self-replicating building that people try to make. No result came out, but still people, the way you can think this. So this is the second application or second group of application. A third group of application I could show that. So there's the idea of the biohybrid robots. So that idea, there's some part of the machine and some part of the biological system. So here you see this one. This is called a micro swimmer. This is a material-based swimmer. It looks like in Bengal, I don't know what is in English, but in Bengali it is called jati, right? So you or you can think of as a Caesar. Oh, what's that? Oh, nutcracker. Yes, yeah. But I never okay, nutcracker. But this nutcracker is also used to crack the lobsters. So to me, it is a lobster cracker then. Okay, okay. So if it is a kind of a Caesar, this Caesar, you just compress and expand. If it is compress and expand, it will move forward, right? That is why it is a material swimmer. But now what you will do, on top of that, you put a cardiac muscle cells. Okay? So what our cardiac muscle cells do? It is compress, expand, compress, expand. So due to that energy, that swimmer can actually move forward in that way. Now, how to actually, how the things will navigate and how will actually control that move? In top of that, you put some engineered, optogenetically engineered neuron cells. What does that mean, optogenetically engineered? So it is a neuron cells, you optogenetically engineer in such a way, if you give a light signal, then it will actually fire. Fire means it is producing electricity. So that electricity actually goes to your cardiac muscle cells, give this, our pacemaker cells has this electrical things, right? So then it starts compressing and things. So through light, you can actually move around these things. And this is actual, it looks like that. So it is completely a cell material biohybrid robot. So that's a starting point. But what you could do, so if you see in the science fiction, okay? Now, so this is Captain America. Okay, so you're listening to my talk. Very good. Okay, so this is Iron Man, and this Iron Man, it doesn't have a human heart. It has a bionic, okay? It has a bionic heart, mechatronic heart, okay? It's a mechanical device. So this is a science fiction, but in reality you can also find that you can connect some of the mechanical device with the body, and this gentleman, he had he doesn't have this left arm, so you put a kind of prosthetics, but this prosthetic is connected with his brain. It's here there's a lot of, it is not shown here, there are a lot of gadgets here, so that, but just by thinking he can actually control its hand, and it is so interesting that even it could take a single grip from these things. So this is science fiction, and this is the reality. In all those cases, when we talk about the biohybrid robots, we started thinking we have some machine parts and put in the human. But when these cell material biomaterials have been developed, and with the synthetic biology, now we could think completely different thing. That is, in the future, probably the machines will have the human part, not the other way around. Okay, so that is, I'd say, it's a possible. So these are some of the possibilities we can think, and probably some of you one day will actually build those things. Now, what I'm going to do, what at the Kolkata, what at the Saha Institute of Nuclear Physics, what my group is doing, right? So if you're a Netflix addict like me, so probably you have seen there is something called Love, Death and Robot in the Netflix. That's a science fiction animation series. Okay, and in this animation series, there is one story, and that is when the yogurt took over. And this is again, it is a science fiction story. And in this story, there's something happened. There is some bacteria called lactobacillus, which can you find in the yogurt. Okay, so when scientists are working on the yogurt, I mean lactobacillus, and suddenly, just by accident, they made some super intelligent lactobacillus. And those super intelligent lactobacillus, what this does, it actually take over the world from the human, okay? And they are our leaders now. And at the end, they made their own space technology and then actually went out from the earth, okay? So that is the story. So what this story has to do with our research? So one goal of our research is, can we make bacteria artificially intelligent? Okay, so artificial intelligence is the buzzword. So the idea of the artificial intelligence, if you take the 90% of the artificial intelligence today, it is based on something called artificial neural network. The idea of the artificial neural network is coming from the neuron. So if you take a neuron and if you give some input in terms of x1 or x2 and you get some output in terms of y1, y2, you will see the neuron always follow a similar kind of mathematical pattern. It doesn't matter, it's a human neuron, it is a neuron from a cat or a dog, it doesn't matter. It always follows that. So when you take this mathematics and just write on a paper by pen, then it looks like that. Okay, so it has some, I'm not going to detail in the mathematics, but just to tell you that if x1 and x2, these are some of the inputs, these inputs is first summed up. How? x1w1 plus x2w2 plus x3w3, something like that. And then it will go through a nonlinear function. Forget about it. But just I'm saying, you go through a nonlinear function and it give you an output, right? Now, so this is, we can call that artificial neuron. Now, what you will do? On a board or a paper, you just write so many circles, connect them with that mathematics. And what you will get? What you will get is something called the artificial neural network. It looks simple, but it can do amazing things. One example, let's say we take a photograph from today's function and then you upload in the do you have Facebook accounts? You're not allowed, right? Before 18, no, okay, yeah. So in the Facebook account, so you give or your Insta or whatever, then they will ask you that you like to tag yourself or you like to tag your friend. So how Facebook is identifying you or your friend? Because they have a face recognition algorithm in their server at the Facebook. Not in your mobile, that is in the server in the US or in China, wherever they have the things. And there, it is nothing but an artificial neural network which has 80 to 90,000 various nodes and connections. And then, whatever the values from your photograph, pixel values from your photograph, you know the pixel values of the photograph, right? Because all of you take the photograph from the mobile, right? So you know what is the pixel values. Those pixel values are your input, and then it does some math, and it gives some the output, and this output is going to match with your previously given photographs on the Facebook. Okay, so basically what happens at the very first time, whatever the output is giving, output is not matching with anything. Then you start changing these W values, okay, and at a certain combination of the W values, you will find this output is going to match your previously uploaded photographs. Okay, so that's how it actually identifies that. So the question my lab asked, so can you engineer a bacteria in such a way they will work as an artificial neuron, and then in a culture this bacteria will interact with each other and you will make an artificial neural network. So the bacterial artificial neural network, if we can make it, then bacteria can do a lot of different kind of the computation. Okay, so we able to develop the first artificial neural network with genetically engineered cells. Our own cells is definitely neural network, but this is the first genetically engineered, some engineered kind of the cell which can actually work as an artificial neural network. And okay, so this is the research journals, came as a its front cover and so on. I'm not going to talk about it, but after we publish this, then there is something called ACM, communication of the ACM. ACM is the Association of Computing Machinery. So this is one of the reputed organization of the computer science, and which gives the Turing Award. So Turing Award is the which is called colloquially, which is called like the Nobel Prize of the computer science. So this nothing to do with the biology; it's a completely computing machinery. They made a story based on some other work and our works. Okay, so half of the story is about our work, and in this story, they mentions a very interesting point that biological computer could outperform silicon-based computer. So this gives us a very happiness in one sense. First, someone is taking that what we feel that it is possible. Some completely computing association is taking that into their account, then it's believes then based because the story is based on our work, which we have done from the Kolkata. So we are very, very happy, and this gives us some the boost. So that reminds me another science fiction series, and this is called the Star Trek. This is Star Trek Discovery. Star Trek has many series. This is the Star Trek Discovery. Interestingly, so Star Trek has, so this is the USS Discovery. That's the spaceship of the Star Trek Discovery, and their computer is not made from a silicon-based computer, but it is made from a biological organism, and that is nothing but the fungus. Okay, so they have a mycelium network, and that is again it is a science fiction. So my lab goal is, can real science back this idea up? I didn't get the idea from there, sister. Please. Okay, don't think that, yeah, many people think I watch the Netflix, get the idea and do the science. It's not like that, friends. But sometimes I get some, so can we do that, right? So one thing, so I have shown that people try to develop some logic gates in the biology, and people actually develop that. But what logic gates is not the whole computer. So if you really want to do computer, then this bacteria or any other cell where you want to make the computer, they have to solve some of the abstract computational problem. Some of the abstract computational problem probably you solve also. And one of them, like, so many of them probably you have in the computer course some Python courses, or I don't know, some other language, right? And so if you write a process, if I give you a computer a problem, a number, like number 3, if number 3 is a prime number, for that you generally write a simple program. Okay, and you give the number to the computer, the program, if the program runs good, then it will say print as a yes. If it is not, it is okay, or if it is 4, it is no, and so on, right? So this is an abstract computation problem because bacteria doesn't understand what is the number is, what is there. So can you actually develop that? So if you want to develop that, first thing, when you actually, how we are going to communicate with the computer. That is, Aditi ma'am asked specifically that in a computer, okay, we type something, but how we are going to communicate with the bacteria at the same problem? How we are going to ask that problem to the bacteria? Okay, so for science fiction, is very easy. So in science fiction, this is the that fungal computer in Star Trek Discovery, and there suddenly a fungus looks like a human, and her name is May. And this is the Tilly, and he's a human crew, and they just start talking. Hey, I have this problem. Can you fix it? This fix it. Science fiction is very easy how they talk with the biological computer. But when we're in this laboratory, when we're trying to make, we have to really communicate with that. I cannot say, hey, how is it going? Okay? You cannot also tell that, right? So we take the exactly same way a computers take that instruction. So when you write a program in the Python, C, or whatever, you are writing in English, okay? But at the machine level, this is nothing but the 0 and 1. You are communicating with the bacteria in the binary, communicating in the computer in the binary, as well as binary means in terms of the electrical. Here, we want to talk within the binary, but chemically. How? So, for example, exactly the computers how they do, they take the decimal number, and each decimal number has some binary counterpart. For example, if you want to ask that if 7 is a prime number, the 7 is represented by 0, 1, 1, 1. Okay? So now, what we do, we take 4 different chemicals. Okay? And these 4 different chemicals, so this is just a beaker or a conical flask. What you do, if you add these 3 chemicals, adding means 1. If you don't add, means 0. So 7, you can ask, you are not adding this 4th chemical, but you are adding these 3 chemicals. Similarly, if it is asking the question, if 4 is the 0, so you are not adding these 3 chemicals because they are 0, and you are adding this chemical. So this way, chemically, we can actually communicate with it, right? And now what this bacteria will do, now bacteria has to print. They have to process the information, has to print that if it is a yes or no. So how this bacteria will say, if it is yes, then bacteria will glow green. Okay, so it will produce a protein called green fluorescence protein, which can machine readable, and it is just a green. You see the bacteria as a green, and if it is, if you want to print no, and it is completely as a red. Okay, so here what I'm trying to show that if you want to do that, so what we engineered, so we developed a set of rules, mathematical as well as biological rules, that how this kind of the system you can map in an artificial neural network. It has a mathematics, you don't have to understand that, but what I'm trying to say, here you see 6 nodes. So, and this X1, these are the chemicals you are adding here. These are your bacteria. So if you can able to engineer this map inside the bacteria so that this input and the output relationship exactly follow this mathematical equation, then your ANN is ready and you can actually give this answer. Okay, so again, so this is just to show that what we developed, something called artificial gene regulatory network. Several genes and proteins are interacting in such a way that input and output relation follow exactly this map. Okay, I'm not going to the details because this is so technical, but we are able to develop that. When you develop that and mix those 6 culture, you can see the results. So here, so if n is a prime number, you say in terms of 2, 3, 5, and 7, the bacteria are glowing green. And any other cases, it is glowing red. So it is exactly identifying the prime number. So we have done similar things. We have done a lot of them. Let's just show a couple of them. So we also asked that if the bacterial computer identifies the vowel, right? So you can write, this is a Python program for that. And this is the artificial neural network for the bacteria. And here you can see that if it is yes, in case of the A, E, and I, it is producing red fluorescence protein. Any other cases, it is glowing green, right? So it can do that. It can do a lot of other math, like if factorial n divisible by n multiplied by n plus 1 divided by 2, and if n, so these are 2 questions answering together. If it is yes, then it is glowing, or if it is no, then it is not glowing. Similarly, we done for the 3 different math problem. Can n square be represented as a sum of 3 factorials? If n square is an interprime, if n is an Amazon prime, and so on, it can. So this your bacteria now actually scaling up and can answer multiple questions. Okay, good. So this is just a yes and no answer. In computer science, this is called a decision problem. So it gives a decision, yes and no. But there is something called the optimization problem. For example, if you have using the GPS, there is a, so to go from the BITM to Sambajar, there is a lot of other paths, but it will give a path, right? One path. And that is the probably the optimized path it will give. So there is the optimization problem. So now let's give an example. What you did. So I know you are very good students. So if I ask you, I'll give you a pie or a pizza and ask you actually cut in 4 cards, okay, and distribute it among people. So you're a good guy. So you'll cut 4 in this way and you'll get 8 equal serving, okay, and give it to you. But if you give a backbencher, a certified backbencher like me, I'm not going to cut in this way. I'll cut in this way. I don't care who is getting small, but in this way I can actually increase my number of friends to give, right? So what I'll do as a backbencher, the biggest piece I'll take, okay, and then 1 big piece I'll give to Aditi. She invited me, okay, and the next big piece I'll give to Suman because Suman actually assured me after this talk he will manage 1 tiffin packet for me, okay. So I'll give these 3 to them, and rest of I'll just okay. So all these things. Now the question is, how many, if I cut 4 state cards, how many pieces I can get, either equal or non-equal? There is a mathematical equation for this. Very, it is called Lazy-Catorus problem. So in this 4 cut, how many maximum number of pieces we can get? The answer is here is 11. So for each number, there is a different number. What is the maximum is a very different number, and it is called lazy Caterer sequence. That is the solution of that particular problem. So here we develop a bacterial-based computer which can answer the same question. The backbencher bacteria can answer the question. So for example, if you have to cut 4, then how we are going to get the answer? Again, this answer we are going to get in the binary. So 11 piece, right? 11 means 1, 0, 1, 1. So you see, in 3 cases, there are 3 fluorescence proteins are expressing, but this is not expressing. So this is giving 1, 0, 1, 1. Similarly, if I want to cut 3, then the answer is 0, 1, 1, 1, means actually 7. So this means this is not expressing any fluorescence protein, others are glowing at a very different colors. So this way, you can actually do that. So when we able to, there are other problems we have done, the adding, subtracting, they can do that. I am not showing them. But when we actually do that, when it is getting published in Nature Chemical Biology a couple of months back, then throughout the world, okay, people are very got interested, and so some of the very prominent science magazines like New Scientist, Physics World, they actually cover our story. At the same time, lot of newspapers and various different languages, Polish and then French and then Spanish and then Italian, they covered all our story. And this, the very good thing is that the work we have done, our students and myself, from this city, okay, and this is giving and this is getting excited by the many other people throughout the world. So that is very, very good for us. Similarly, definitely the local newspapers also covered, our national newspapers, Anandabhajar Patrika, they covered. That one very interesting thing I learned from here, when I put it in the Bengali, I mean, whenever they actually publish this, so a lot of people in our institute, lot of people like vegetable vendors in the Hatibagan market, okay, they started asking about this story, and they started asking is a lot of very fundamental philosophical question, and that is actually, this give a new idea to us that it is not that the common people don't like the science, but this is the common people like the science, and they're really excited and they're asking this story, and that's why I take the courage to actually talk a research results with the students like you, right? So that is very interesting for us. So now I'll show another and then I'll stop. So here, you know, this is a maze problem, right? So this is the children can actually solve those problem very easily. Now, if you are not a muggle, but you're a wizard, you have a different maze for you. Try wizard maze, okay? If you have seen Harry Potter and Goblet of Fire, there is a try wizard, right? Yeah. Now, so Harry Potter can't solve that. So the whole point I try to make, a maze is something, either a muggle or whatever. Harry Potter is a kid, so a kid can solve a maze problem. But if you give this problem to a computer or to a robot to solve the maze problem, it is very, very difficult for them. Why? Because we don't know how brain gets very easily solve that, because we don't try all the options. We just do 1 or 2 and we solve. But if you give it to the computer, you have to give an algorithm through which it has to solve. So that is why you see in 1971, this is the first maze-solving computer. It looks very cumbersome, right? So that's why we try to think that can we make a maze-solving computer with the bacteria? But in this case, we have taken a very simple maze. It is just 2 into 2. So you have a source and destination, and 2 into 2, you can have 16 different maze problems. 13 cases there are no solution, and 3 cases there are solutions. So here you see, when you give this problem to the bacteria, again in the chemical and the binary, you will basically see in 13 cases it is not glowing, in 3 cases they are glowing. So this is saying that where there is solution and where there is no. So again, when we publish this paper, this is also some of the very important science magazines like MIT Technological Review, New Scientist actually talked about it, and New Scientist actually told, the MIT Technological Review will be that after 13 years, some of the work which has been done from the India is getting featured in their things. And they also write some very interesting thing. A group of at the Saha Institute of Nuclear Physics in India took things a step further. So this is always, very exciting for us. It is. So the whole question is, you can ask after all this talk, who cares? Okay. Why we are going to do that, right? So now, why we are going to do that? So when people talk about the microcomputers, so this is the smallest computer of the world made by the IBM. They call this microcomputer, but you can see it is the millimeter or the centimeter range, right? So it is this is one of the set of the smallest robots that can also in the centimeter or the millimeter range, right? So which basically means actually in the micron level there is no computer present, right? So, but a bacteria is exactly like the 2 to 5 microns. So our diameter of our hair is around 25 to 50 micron. So it is the 10 to 20th less a bacteria's length is like that, right? So in that you cannot have a computer, okay? So then if you can make this bacteria as a computer which can take some of the decisions by themselves, okay, and then the computation, so you are getting completely a new technology at the micron level, right? And then you can think about the seamlessly many things. For example, when I shot the Fantastic Voyage, we probably don't need a human to go there. You make some bacteria intelligent, you inject it, this bacteria will take a decision what to do, right? So those kind of the things is possible. There's a lot of other applications you can actually think of. Only the sky is the limit. It just depends on that. So this is one of the reason that we would like to develop this kind of technology. Second is much more fundamental scientific ways. Okay. So do you know who is this guy? Richard Feynman. Yeah, exactly. So one of his famous quotation is, "What I cannot create, I don't understand." So now let's think about that bacteria. When you're talking about the chemotaxis, it has to, so when you talk about the intelligent, which always comes, as I said, this guy has a very intelligent guy, and this guy is like a donkey. This way we actually compare. But what is the intelligence, right? Even I'm a donkey like intelligence, but still I have some intelligence, okay? Right? Whatever it is. So if the bacteria has intelligence? We may not understand that intelligence, but we can see it has some problem solving capacity. It can take a decision when to swim, when not to swim. Now, if you give some, with the food, with the same food, if you give some phenol, which is poisonous to the bacteria, that is, bacteria cannot understand that. Bacteria actually go there, right? It cannot differentiate between the good and bad food. You take an amoeba, another single cell organism. They can differentiate between the good and bad food. It is not going to go towards the phenol. Okay, it stops. It will search for other direction. Now, so that is another level problem solving, increasing the problem solving. Still, it is a single layer organism, a single cell organism. Now, here's the food, good food, and your amoeba is going in this way. You give an obstruction here. What will amoeba do? It will hit the obstruction and stays there because it doesn't know what to do. Instead, you replace with the paramecium. It is another single cell organism, right? In paramecium, what it will do? When it gets an obstruction, it hits there, it's come back, change its direction, swim again. So it's trying to solve the problem in this way, right? So all of these cases, they are a single cell, they have no neuron, they have nothing, but they are solving this. So this is the primitive level of intelligence. So when we are engineering the bacteria in such a way, we're stitching molecules by molecules, and we're doing that, it can do a prime number or a vowel and so on, or a maze problem. That means we are building that intelligence, okay, by molecule, through which we'll try to understand what is the origin or the mechanism of the intelligence itself, or we'll probably try to understand what the intelligence itself, okay? So now, this kind of the bacterial computer can seamlessly integrate in many things. It can overperform a silicon-based computer at the micron level, but this is not going to give you a computer through which you can do your Facebook or Instagram. Okay, so that requires a general purpose computer. So how we may want to solve, we haven't solved it, the problem, but what we believe, so this is just 1 week back, this is some of the neural progenitor cells. So these cells, we are changing it to the neuron, and this is a kind of a neural network. So actual neurons, it is not in the brain, it is in the dish, okay? So if we can control this, okay, and connect with the computer, so we do believe that one day we able to develop a real AI, okay, which has the human-like intelligence. That's our belief, okay? We have started, probably you will end that at a certain point, and maybe after 20 years, a person will come here, and that's not a human being, but probably that's an engineered organism is going to talk about human, okay? And with that, I thank all of you for your attention, and this is my group, and thank you very much.
So intelligent bacteria, now we are all ready for you, right? If you have any queries from the speaker or any feedback for our speaker, please raise your hands. Yes.
Good morning, sir. I'm Divsha Ray from Gokhale Memorial Girls School. I'm in 11th grade. And my question is that as students, we don't get a lot of exposure to fields like biophysics. So how do we go about starting off if we want to go into this field?
So in the biophysics, so I think as a student now you get a lot of information, okay, right? But Google, right? That is the whole thing. So that is so you start looking at the biophysics and then look at what you do in the Indian biophysics. So that is the one way. So all you want to get some information, start with the Google and then use your intelligence to divide which is a proper information, which is not. So start with the biophysics. It doesn't matter which area you are studying. So you can have a degree in engineering, you can have degree in medicine, you can have degree in physics, chemistry, biology, anything. And then at a certain point, as you go along, you actually start getting, you start getting along. So maybe if you are interested in the biophysics, you start doing some internship on the biophysics. When you are try to do your PhD, you choose the biophysics related things, right? So, and interestingly, in my background, my BTech is in the petrochemical engineering, and my beloved madam is from pharmaceutical engineering, right? So you know that how these things have come together. Yeah, ma'am is like my mother, so it's not a thing. So this happens. Okay, so you can go from anywhere to anywhere. It depends what you want to do. Okay.
Okay, thank you, sir.
Yeah, I'll come.
Good afternoon, sir. I'm Sharona Banerjee from Gokhale Memorial Girls School. I am in grade 11. So you mentioned about certain about chemical formulas that are used to integrate binary codes to convey the informations to the bacteria. But is it even organically feasible integrating the binaries into the biomolecular basis even?
Okay, very good question. So if you see, our life is nothing but a sea of chemistry. So at each moment, at any of our single cell, okay, it is probably happening 30,000 different reactions per minute. Okay, so that is a completely the chemistry. So how biology solves this problem? In real biology solves the problem in very different ways. So they have most of their analog, okay, and many of the cases they also use something called the binary-like system. Now, what your question is very, very important. If there is a chemical, there is always an increase or decrease in the concentration. So it's analog. How would do that? How our neurons solve that? Neurons solve that. The mathematical equation I showed: x1w1 plus x2w2. When all this addition reaches a threshold, then only it fires. So it is a binary, but it is taking this. So that means if x1 is less, but x2 is high, then still it can fire.
Are the mathematical equations understandable or segregated by the?
Yeah, our brain is actually doing that. So we know that there are some. So mathematics is an abstract thing. We just used to understand that scenario. So our brain is exactly doing like that, right? So when I'm bringing that in the bacteria, the same mathematics, which is suggesting is a threshold like 0 and 1, right? But your input is coming in the analog, right? So it will add them up, and if it goes above a threshold, then it will fire, then it will give the answer. So even it is the analog, it will take as a 0 and 1. So instead of the 0, if you add a little bit of the chemicals, then it is 0, right? So the same thing actually when it's called the binary, even our electronics is not binary in that level. So for example, when you say the 0 voltage, means 0 in actual gate, it is not 0. It is 0.1, 0.2, 0.3, 0.8. It can, so sometimes people take 0.8 volt as a 0. Anything below 0.8 is a 0, and anything above 5 volt as you take as a 1. So nothing is binary in the whole universe. It is just an abstraction, but this math can actually make a real binary, an analog to a binary phase. Yeah.
Good afternoon. My name is Tiyasha Datta. I'm from Ashok Hall. Actually, my question is that is it possible to design the bacteria in such a way that if it is somehow able to get into the human body and control its mind?
Control its mind.
Yes.
Yeah, that always. At this moment, there is a lot of research. People know that our gut bacteria is controlling our mind. Right? Controlling our mind means there is a connection. This is called the gut-brain axis. So there is some chemical, some way. Not people understand very well, but we know that if you change your gut bacteria, that is going to control your mind. So people have in a depression. If you give a different kind of gut bacteria, the depression will go away, and different kind of gut bacteria or depression will come. So that is there already. Now, what you are asking that if you can control, but that this moment it is like simple. We control. I mean, definitely, if it is the possible, then there is always a possibility that they control that. Means see, when you asking or anyone you asking if this is possible or not, the answer is very simple. It is possible if it is not limited by the natural laws. You cannot make a perpetual machine. Means that you cannot just give no energy and the energy stops. So that is because this second law of thermodynamics actually stops that. Any other thing is possible. So you are in which class?
Class 9.
Class 9. My son is in class 8. So when I actually told him about this problem, and he said that why not you design some of the bacteria and inject it in my head, so I don't have to learn the math. The bacteria will learn the math for you and do it. That's probably possible. One day you will do that. Okay. Yeah.
Good afternoon, sir. I am
Yeah.
from MBSV Diksha Bajaj, class 9. I have a question. Yes, AI is evolving, but how is it possible to make bacteria intelligent? Like, I know it's microscopically it's possible, but how? Like, it's very difficult, right? So what is the process of that?
Okay, so the process I said, so everything has a rule. When you are talking about the artificial intelligence, it has a mathematical rule. So whenever talk about AI is nothing but statistics. So if you really want to learn AI in the beginning, so you should actually go either the rule of the goes of the statistics or the math. So the math of the ANN. So this is coming from a theory which is called universal approximation theorem that suggests that a particular form of the ANN can solve any problem. Right? That's a mathematical theory. So if you want to make that things in the bacteria, what we need to do, we need to engineer the bacteria such a way that follows that math. Because the same thing is happening in our brain too. So that our brain. So I showed in just for a moment. So here is the neuron. So this scale bar is 75 micrometer. So one neuron or interactions maybe some 100 micrometer. 100 micrometer is very less. So actually what is happening in our brain, that is also microscopic level of the cell. They connect with each other and that develops me or you or any other, whatever the intelligence or whatever we have. So if that's possible in the bacteria, if you can bring a lot of those things to the bacteria, then it's definitely possible to go to the intelligence, right? So how much, we don't know. It depends on the how much. But when we believe that if we start engineering this neuron, then we go to much intelligent things we can actually develop. Yeah.
Good afternoon, sir. This is Titisha Das from Loreto House, 11th grade. My question is that, so you mentioned that one of the limitations of developing an intelligent bacteria is that suppose there's a phenol and bacteria cannot understand if it's a good food or the bad food, it will go towards the phenol. But amoeba can actually differentiate between the good food and bad food and it will not go towards the phenol. So why can't we develop intelligent amoeba instead, since in some way amoeba is more intelligent than bacteria? So why not amoeba and bacteria?
Okay, so the whole point is that why we are building that, right? So amoeba is much bigger than the bacteria. So if you want to micron level things, then you need the bacteria. Second thing is the amoeba is the animal. So bacteria can actually stay at every environment, right? Okay, so then it is much more robust. So use those things. But if you can find a reason that okay, for this particular thing I need to develop the amoeba for that, we can do that. So that it means we means not us, you. Okay, you can do that. So the whole thing is like why so it is not that what you suggesting that you make an intelligent a more intelligent. Okay, that is not the goal. The goal is which is not intelligent. So can I make the bacteria in such a way it is not going to go towards the food. So that if you make in Bengali which is called gadha pitiye ghoda kora, that is much more than the using a horse, right? So so that's why you choose the bacteria. Yeah.
Good afternoon, sir. I'm Aratrika Sena from the Heritage School, 11th grade. I wanted to ask if an injected intelligent bacteria in a human malfunctions, what are the side effects that can be visible?
So we haven't, so that is why whenever something comes, so we haven't done that. Right? Our goal is definitely not to use that as per the bacteria. Our goal is to how complex computation this bacteria can go. But what I'm trying to say that this bacteria can be used for that, right? So there are many companies who use the bacteria. There are the 3 bacteria which is FDA approved. One is E. coli, another is an attenuated salmonella, and third one I forgot. So that can be used as a drug delivery vehicle for human body. So it is not harming the human body in terms of the immunity and everything. So we know there are passive vehicles. Now, if you engineer those bacteria as an intelligent one, now those bacteria can take decisions. Now, when you're saying that if there is something goes wrong, then we have to understand what can be. One thing is that it is not working properly. So that is why this is, if you think about the computer, this is a replicative computer, okay, which basically means there is millions of the cells are taking the decisions and so on. So if a set of cells got wrong, okay, means not doing anything, but the other cells are actually doing the whole thing. So in terms of the computer science, it is called the distributed computing. People use distributed, the computation has been distributed among many parts, so that if there is something wrong happens, the other will be taken care of it. But if you say in terms of the science fiction, suddenly something like this lactobacillus taken over the world, okay, we don't have to go to that intelligence. Human stupidity is good enough to destroy us.
Good morning, sir. I am Devanjali Banerjee, currently studying in grade 9th of the BSS school. I had this question. It's like, even if we artificially imitate bacteria as a living neural network and we inject it into a person's body, is it possible that that bacteria can bring a structural change in the DNA pattern in order to cure cancer instead of the radiation therapy or any other therapies we use?
Okay, so when you're saying the genetic pattern means people, not for the cancer, but for other things, it is something called the gene therapy. So if there is a congenital genetic defect, the people use the virus, okay, and even started using the bacteria, so they actually go, but mainly people use the virus so that it goes inside and correct that gene. So there is some of the treatments are available. I don't know if it's available in India, but in the Europe and US, some of the gene therapy treatments are available. So, but the whole question is, so how people using the bacteria, because they use something called siRNA. Okay, so that is a part of the kind of the RNA. Those RNA molecules actually stops a cancer pathway. So people developed that probably 30 years back. People got Nobel Prize for that, but still it didn't come. It came like 2015 is the first thing. So one thing is the delivery. They cannot deliver because that degrades. So with the bacteria, you can send those shRNA. Those shRNA or siRNA actually connecting with the genetic network of the cancer cell and actually kill those. In that way, people are doing that.
And even if a bacteria is injected into a body, artificially transmitted, artificial one, after completing its purpose, is there any way to remove that from the body, or is there no way to remove it from the body after it's completed its purpose in the body?
Yeah. It can be. So you can engineer the bacteria. So nothing will stay in the human body for the whole life. So you can actually, so when you're actually injecting, you are probably not using the replicative thing. You actually mutated the bacteria in such a way, it is not replicating. If it doesn't replicate, it will actually degrade by the whole system. So there's a lot of ways to do that. So that is, I think, that the people who are using for the medical purpose using the bacteria, there is a lot of rules to how to actually do that. But you can program any bacteria to how long you want to actually stay alive.
So, can I add a question to it? So, are we injecting different bacteria for like every different problems in our body, or like a single bacteria is being injected and it is able to like solve all the problems in our body, like different diseases.
No. So first of all, this is a so when you engineered an intelligent bacteria, they can do many things. So I just talk about the body, but it could be think about on the Mars. When you are trying to build a road or something, you cannot give the instruction to the bacteria. So they have to take their own decisions and make that. So what we are building bacteria, which can take their own decisions and can do. But what you are asking this question, a very specific problem. We are not working on the specific problem, but if you work or any other work, both are possible. So, but both means a bacteria can solve 3 problems probably. A bacteria can solve 10 problems, right? But how many problems? We don't know. It depends on thing. What you want to do with it.
Okay, like we have to mutate it first, and then it, like
no, you engineer first.
we engineer
Yeah,
the bacteria first, and then we like understand it in the person's body. So like we can engineer the bacteria to work on like a wide range of diseases and then inject it in the body.
No, it depends. Because why do you look for the different disease? Maybe you engineer a body for a simple one disease, okay, and then it is much more easier. So administration is the thing, but it is also not only in the body. People can think about the self-healing bridge. So you engineer the bacteria which sends some enzyme and actually make the cementation. And if you can do this computation, then the bridge will, whenever there is a micro crack, they will actually heal by themselves. So there's a lot of other things. Forget about the human body. So there's a lot of other applications you can also think about.
I know we still have a lot of questions, but we need to wrap up this session here. You can stay back for a while if you want to interact with sir.
Yeah, if Suman is going to give me a food packet, I'll stay another 1 hour, no problem.
Yes, sir.
Yeah. So I'll answer your question, okay, after this.
So, Sangram, I have a different question. I have a question like, I was just thinking that they have a lot of mechanical properties because bacteria moves and then it moves in a particular direction. So if it is moving in a particular direction means it will be having a vector. So can we do different type of calculations by using the mechanical properties of bacteria other than the chemosensing?
Means in terms of the input you want to give
in terms of input.
So we haven't done that because one of the limitation is how many. So what are the so output I can say. So we have done here I just showed fluorescence protein, but we have done output in terms of the length of the bacteria. We can actually control anything we can do on the output.
So just like vector algebra, we do a lot of calculation based on a particular particle moving in a particular direction.
Okay, that probably we can do. I haven't thought about it, so I have to actually think about it.
Thank you for your questions and feedback. Your interactivity really makes it worth organizing such events. And now I would request Professor Shumon Mojumdar, Director R&D Ectalis and Honorary Treasurer, Royal Society of Chemistry, Eastern India Section, to conclude today's session by proposing the vote of thanks.
First of all, thanks everyone for your participation and engagement. The talk was so insightful. For a timing, I went into the world of bacteria. So it's very interesting, insightful, and for you students, it's a new horizon. Basically, there is an orbit shift in research, and this particular field of synthetic biology will take you to a completely different domain where everything is interdisciplinary. So there may be mathematics, there may be chemistry, physics, and whatnot, biology for sure. So with that, I would like to conclude the session. I would like to thank Sangram for a very, very insightful talk, and this will also give the students a lot of food for thought for their future career and what they should pursue, and that will be interesting. Thank you, the director, sir, for for collaborating with the Royal Society of Chemistry, giving this opportunity for so many years to hold this Niroprova Memorial Lecture. I would like to thank the members of the members of Royal Society of Chemistry, Professor Shiprana Datto, for being here and talking about the background of the society and how we are actually inculcating the science in students and in urban and in the rural region. And also like to thank Aditi for taking all the pain to organize these things. It's sometimes very difficult to put everybody together. And at the end of it, BITM for having these type of platform and giving students, teachers, and scientists a platform to interact, talk to each other, and take science forward. So thanks. Thank you, everyone.
Thank you to all the schools. You're free to visit our galleries if you have time today, but please remember to collect the small refreshment packets that we have from the ground floor cafeteria before you move to the galleries. Thank you very much. Thank you all.